Additive manufacturing of metallic components, process, structure, and properties. Since its inception, significant progress has been made in understanding additive manufacturing processes and the structure and properties of the fabricated metallic components. Because the field is rapidly evolving, a peri- periodic critical assessment of our understanding is useful, and this paper seeks to address this need. It covers the emerging research on AM of the metallic materials and provides a comprehensive overview of the physical processes and the underlying science and metallurgical structure and properties of the deposited parts. The uniqueness of this review includes substantive discussion on the refractory alloys, precious metal, and compositionally graded alloys. Succinct comparisons of AM with welding and a critical examination of the printability of the various engineering alloys based on the experimental and theories. An assessment of the state of the field, the gaps in the scientific understanding, and the research needs for expansions of AF on the metallic components are provided. Additive manufacturing processes build three-dimensional parts by progressively adding thin layers of the metal materials guided by the digital modems. This unique feature allows production of complex or customized parts directly from the design without the need for expensive tuned for or forms such as punch dies or cutting molds, and reduce the needs for many conventional processing steps. Integrate parts due to the design can be made in one step without the limitation of the conventional processing methods. Straight cut, round hole, or round hole, or commercials, sharpies, seat, to buy, to being. In addition, a significant reduction in the parts count can be realized by eliminating or reducing the need to assemble multiple components. Furthermore, parts can be produced on demand, reducing the inventory of spares and decreasing lead time for critical or obsolete replacement components. For these reasons, IM is now widely accepted as a new paradigm for design and production of high-performance components for aerospace, medical, energy, and automotive applications. Aerospace examples include complex fuel injector nozzle that previously required assemblies of the multiple parts and high and lightweight engineered structures that result in a significant cost savings. Medical and dental implants produced by AM offer significant improvements of the integration, biocompatibility, and the possibility of the patient matched device and derived from the patient's own medical imaging. Mixing, uh, mix, mixing and three-linked burner tips made from high-temperature materials in complex shapes save energy extended components lifetime and reduce system repair and downtime. Automotive applications include prototyping and the rapid fabrication and rapid of industrial hardware, such as punch, dice, and custom tooling. Significant advances over the past 20 years in the constituent technologies of AM metal processing, including lower cost, reliable industrial laser, inexpensive, high performance computing hardware and software, and the metal powder feedstock technology have enabled it to become a state-of-the-art processing method. It has now reached a critical acceptance level, as evidenced by rapid growth in the sales of the commercial system. AM metal technologies developed in the national laboratories, university and industrial research laboratories is now being demonstrated and adopted by industry with certain applications have reached technology readiness level of the fully certified production. Most have done so through brute force certification of each individual part type, material, and process. A more thorough understanding of the feedstock materials, process structures, properties, and performances are desirable desirable to produce defect-free, structurally sound, and reliable AM parts. Additive manufacturing has grown from the field of rapid prototyping, which was developed more than 30 years ago for the producing non-structural components, largely for design purposes. The newer field of the metal AM has the ability to produce hard to manufacture components in the complex structural shapes that are difficult or impossible to fabricate by conventional means at a direct replacement of conventionally manufactured components. Metal AM is now finding acceptance for the critical applications such as medical implants, aerospace, and in many other fields with a clearly demonstrated ability to produce complex shapes. There are, however, some metallurgical difference between the conventional and IM components, such as mechanical anisotropies, resistant stress, residual stress, residual stress, and defects unique to AM processes that must be addressed for the critical aerospace application, particularly those components that require exposure to high temperature fatigue. Applications such as the fuel injector and other highly complex components are now being to make this way to certification. Why these are the high performance of components such as the turbine blades, for example, are at an earlier state of the development. The AM for alloys has its origin in the metal powder technology. High energy beam welding, cladding, and prototyping. Existing knowledge based in these technologies is here helpful, but does not address many of the important features of AM. In the many decades of research efforts that have resulted in the relatively mature knowledge base of the welding and casting is Any clues the path forward research and development of the metallic materials is going to be a long and tortuous road. road. The journey has already begun with a growing interest for research, particularly of the metallic materials. The increasing number of publications and several reviews on the processes, microstructure, and properties of the AM parts are available in the literature. Since AM is relatively new and rapidly evolving, a periodic critical assessment of our understanding is necessary, and this review seeks to fulfill this need. The review focused on the aim of the metallic materials, particularly the process, structure, and properties of parts. Solid-state processes, such as sheet lamination, or those that really released primarily on cold compaction, binders, or infiltration or brazings are not within the scope of this review. Apart from this, apart from its comprehensive coverage of important and engineering alloys, this review includes IM for the special material including free refractory alloys, precious metal, and compositionally rate alloys. Also, a succinct comparison of the AM with the welding is presented to highlight the similarity in the physical processes. The mature knowledge base of the welding and metallurgy can provide powerful synergistic benefits for deeper scientific understanding of the AM. Furthermore, the review seeks to critically examine the printability of the various engineering alloys based on the current knowledge of base of the AM, metallurgy, and fusion welding. Where possible, this review emphasizes quantitative understanding in a form that can be used for back-of-envelope calculation to obtain reusable insights. It is hoped that this work will be helpful to understanding the current state of the technology, the gaps of the scientific work, and the research needs most beneficial for the advancement and expansion of AM for metallic materials.